Okay, so for problem number 1, we're asked to prove this by induction. So remember, for induction, we have 3 steps. The first is to show that it works for some initial value. So we're going to show for n equals 1. So if n equals 1, the left side here is just that single term, which will be 1 over 1 plus 1 times 1 plus 2. We got to show that that's equal to 1 over 2 times 1 plus 4. Well, 1 plus 1 is 2, and 1 plus 2 is 3. So 1 over 2 times 3 is 1/6. On the right side, 2 times 1 is 2. So 1 over 2 plus 4 is 1/6. So it is true for n equals 1. Step 2 is we assume it's true for n equals k. So what we're saying there is the sum for I equals 1 to k of 1 over k plus 1, k plus 2 is equal to k over 2k plus 4. We assume that to be true, so there's nothing we have to do with that other than state that we assume that to be true. Then we have to prove that given that, with this assumption, that it's true for n equals k plus 1. So we're trying to show this for the summation from n equals 1 to k plus 1 for 1 over k plus 1 times k plus 1 plus 2 equals k plus 1 over 2 times k plus 1 plus 4. So let's work on the left side here first. We're going to split this summation up into the summation from, that should be an I equals 1, not n equals 1, from I equals 1 to k of 1 over k plus 1, k plus 2, plus the next term of 1 over, come on, k plus 1 times k plus 1 plus 2. So let's do the algebra on that side first. We can replace this with that assumption from up above, not that one, but this one from up here, k over 2k plus 4. So the summation up to k is k over 2k plus 4. On this side, we'll do some math. K plus 1 is k plus 2. K plus 1 plus 2 is k plus 3. To do some combining here on the first part, k over 2k plus 4, I'm going to do some factoring in that denominator. I'm going to factor out a 2 to get 2 times k plus 2. Plus 1 over k plus 2 times k plus 3. Now, to add those, to combine those, we have to find common denominator. This fraction has a 2 in the denominator that this one doesn't, so I got to multiply numerator and denominator by 2. This fraction has a k plus 3 in the denominator that this first one doesn't. So I multiply numerator and denominator over here by k plus 3. So this over here ends up being k times k plus 3 is k squared plus 3k over, and I'm just going to leave these out in factored form, 2 times k plus 2 times k plus 3. Plus, over here it'll be 2. 1 times 2 is 2 over 2 times k plus 2 k plus 3. And so those add right together. The k squared plus 3k plus 2 over our common denominator. 2 times k plus 2, k plus 3. Let's look now at the right side and see what happens when we simplify that. Hopefully we get the same thing. So we've got k plus 1 here over, let's distribute the 2. So 2 times k is 2k, 2 times 1 is 2, plus a 4 down there. Well, this is 2k, 2 and 4 make 6, so 2k plus 4, 6. So we got k plus 1 over 2k plus 6. I'm going to factor out the 2 in that denominator. So I've got k plus 1 over 2 times k plus 3. Now to make these fractions equivalent, this one had a k plus 2 in it. So I'm going to multiply numerator and denominator here by k plus 2. So my denominator is 2 times k plus 2 times k plus 3. If I FOIL out this numerator, k times k is k squared. K times 2 is 2k, 1 times k is 1k, that's 3k, and 1 times 2 is 2. And we notice that does give us the same result we had over here. So we have just proven that by induction, that if it is true for k, for n equals k, it must be true for n equals k plus 1. Binomial expansion. Remember, our binomial expansion was n over r of a to the power of n minus r times b to the power of r. R is whatever the term is minus 1. So if we want the third term here, r is 3 minus 1, or 2. N is just this power. So our third term is 5. Choose 2. 3 minus 1 gives us the 2. Of a, in this case, is the 2x. So 2x to the power of 5 minus 2. B, in this case, is negative 3. So this will be negative 3 to the power of 2. Five choose 2 is 5 factorial over 2 factorial times 5 minus 2 factorial. So the 5 factorial is 5 times 4 times 3 on down. 5 minus 2 is 3 factorial. That's 3 times 2 times 1. And of course, the 2 factorial is 2 times 1. Well, the 3 is here. 3, 2, 1 cancels out. 5 times 4 is 20. 2 times 1 is 2. So 20 over 2 gives us 10. 5 minus 2 here gives us a power of 3. So 2 to the third is 8. X to the third is just x to the third. Negative 3 squared here is 9. So 10 times 8 times 9 is 720. X to the third. That is the third term of that binomial expansion. Any questions? Okay. So, today, our new topic, we're going to talk about counting principles and basic probabilities. This kind of builds on what we were doing, with the binomial term that we talked about, combinations and permutations. We'll talk about those as well. That's a special type of counting that we're going to be doing. But let's take a look at just basic counting. Something called the fundamental counting principle. What the fundamental counting principle states is that if we need to choose more than one item from possibilities, whether they're the same group of possibilities or different groups of possibilities, that the total number of possibilities is just the product of the possibilities for event A times the number of possibilities for event B. Let me give you an example of what that means. Let's say you're trying to choose breakfast. And you're going through a cafeteria. Your cafeteria gives you can choose one each of beverage or drink. You can have milk or orange juice. You can choose one meat. You can have ham, bacon, or sausage. And then you can choose eggs, fried, scrambled, hard-boiled. So you have 3 items that you can choose there. First item is our drink. Second is your type of meat. And finally is your type of egg. So how many different meals can be made? How many different meals could be selected? Assuming that you did have to choose one from each category. So the option of not taking a meat or not taking an egg or not taking a drink is not an option. You will take one from each. Well, for drink, you have 2 choices, milk or orange juice. So there's 2 choices for drink. For meat, ham, bacon, or sausage, there are 3 choices for meat. For eggs, fried, scrambled, or hard-boiled, there are 3 choices for eggs. So what the fundamental counting principle tells us is to get the total number of possibilities, we just multiply those possibilities for each of those categories together. So 2 times 3 is 6, times 3 is 18. So there's 18 different possible meals for that breakfast that can be chosen from those options. Another possibility might be a test. It is 6 questions. Multiple choice. A, B, C, D, or E. So 5 choices each. How many different combinations of answers are there? Well, you have 6 questions. 1, 2, 3, 4, 5, 6. So we have to look at the possibilities for each of those 6 questions. Well, there are 5 choices for each question, A, B, C, D, or E. So question 1 has 5 possible answers. Question 2 has 5. 3 has 5. Each of them has 5 possible answers. So the fundamental counting principle tells us to get all of the possible sets of answers, we multiply them all together. So that's going to be 5 to the power of 6, which is simply 15,625. So it's 15,000 different possible combinations or permutations of answers. So if you're just going to guess on that multiple choice test, There's 15,625 ways to guess. So your chances of guessing them all correctly are pretty slim. Now the other side of that, let's look at another test. But this one has 10 questions. And it's true or false. So now for each of those, rather than drawing this out with 10 questions, I know that each of those questions has two possibilities. So it's going to be 2 times 2 times 2 times 2 times 2 all the way up to question 10. So that's going to be 2 to the power of 10, or 1,024 possible combinations of answers on that test. Only 6 questions on the multiple choice gave over 15,000 possibilities. The true and false with even 10 questions only gave just over 1,000 possibilities. Again, that's because there's only 2 choices for each of those items. License plates are kind of an interesting application. In the state of Wisconsin right now, license plates are 7 digits long. At least new license plates are. The first 7 digits must be a number. The last 3 digits are a letter. Unless, of course, you get vanity plates or custom plates. The randomly assigned ones are arranged like this. And actually, I think they just switched them so that the letters come first, but that's okay. We'll get the same probability. And there's a restriction. The first number cannot be 0. So it can be any digit 0 through 9, except for the first one. It can only be 1 through 9. So if we look at this, our possibilities for the first one, there's 9 possibilities. 1 through 9. For the second one, there's 10, 0 through 9. 10 and 10 again. For letters, they can be any letters. So there's 26 combinations for the first one, or 26 possible letters for the second one, and 26 possible for the third. And we multiply those all together. This gets rather large. 9 times 10 times 10 times 10. That alone is going to be 9,000. Times 26 times 26 times 26 gives us 158,184,000 combinations. So close to 160 million possible license plates that can be issued with that combination. Should be adequate because there's only 5 million people in the state of Wisconsin. But they did have to bump it up. It used to be only 3 numbers and 3 letters, and now they had to bump it up to 4 numbers. Okay, so we want to look now at what happens when we do some standardized types of choices. What we've been looking at so far is actually called permutation. Because the order you put things in matters. For the license plate, (3124) MPG or 1324 MPG. Those are different. Those are unique license plates. The order of those numbers, switching the 1 and the 3, changes the license plate. It makes it totally different. So in a permutation, the key is the order of selection, or sometimes just the order of arrangement. Write that legibly. Matters. If they're arranged in a different order, it's a different license plate. Well, we're going to assume that they are always going to be arranged in the order they're selected. So we just have to talk about the order of selection. We're not going to rearrange them later. Now for a permutation, we're going to define something called with replacement. And without replacement. And we'll talk about this a little bit more when we get to our probability section coming up. But if you think of marbles in a box, if we have 3 red and 2 blue marbles in a box. Well, if we look at that, there are 5 total marbles in the box. 3 out of those 5 are red. So that's the ratio of red. If we take a marble out, if we select a marble for something, well, if that marble is red, if we don't put it back, if we set it off to the side, now there's only 2 out of 4 marbles in the box that are red. That's a drastic change. If that first marble was blue, there's still 3 red marbles in the box, but we are still down to 4. So there's 3 out of 4 marbles that are left in the box are red. Still a drastic change from 3 to 5. This is what we refer to as without replacement. The same marble can't be repeated because once you draw it out, it's not reused. The same could be thought of for our number combinations. If we have a 4-number combination, a permutation would be there's 10 possibilities, 0 through 9 for the first number, 10 for the second, 10 for the third, 10 for the fourth. That multiplies up to be 10,000 combinations. But what if numbers cannot be repeated? So once I use a number for the first digit, I can't use it again in the rest of the combination. So it's still a 4-number combination, and there's still 10 possibilities for the first digit, 0 through 9. But now for the second digit, whatever that first digit was, I can't use that again. There's only 9 possibilities there. Think of it as putting the digits 0 through 9 in a hat, mixing them up and drawing one out. Up here, we drew it out, we recorded it, we put it back in, mixed them up again, so that when we drew the second one, it's possible that it could be the same digit. Down here, we drew out the first one, we wrote it down, then we throw it away. We don't put it back in. It can't be chosen again. So there's only 9 left in there to choose from for the second one. And now we've chosen 2, there's only 8 possibilities for the third, and 7 possibilities left for that fourth digit. So we multiply those up, 10 times 9 times 8 times 7 gives us 5,040. This one here was with replacement. We chose that digit, we put it back in so it could be chosen again. This one here is without replacement. So the with replacement basically just comes down to our basic counting principle. In fact, you can see here, this was just 10 to the power of 4, 10 to the power of the number of digits we needed to choose. We're going to focus more now on this without replacement, where it cannot be repeated. One way of doing, one example of looking at this is, let's say we have 5 trophies. And we want to arrange them on the shelf. This is obviously without replacement, because once we put a trophy in one slot, we can't put it somewhere else. It can't be in 2 places at once. So when we go to arrange them on the shelf, there's 5 trophies, so we're going to have 5 spots to put them in. For the first spot, there are 5 choices possible. The second spot, there's only 4 choices possible. The third spot, there's only 3 choices left. The fourth spot, there's only 2 left. And finally, at the 5th spot, there's only 1 trophy left, so only 1 choice. Now, you might look at that and realize that this is our factorial notation. 5 factorial is what that comes out to. That ends up being, what is that, 120? Yeah, 120. So there's 120 different ways to arrange those trophies on the shelf. So the notation we're looking for here is permutation. It's sometimes written as NPR, or sometimes written as P is a function of N and R. They both mean the same thing. N is the total number of choices. To choose from. And R is the number to be chosen. So if we look up here, this example was a permutation of 5 items where we are choosing all 5 of them. So in that case, that just ended up being 5 factorial, or n factorial. But we don't always deplete the whole items. We're not always going to put use up all of the items we have to choose from. So let's do a different example. Let's say we have 10 trophies, and we're going to arrange 5 on a shelf. Actually, let's make this more interesting. Let's arrange only 4. 5 is right in the middle, so the 4 is going to be a little bit more telling for us. So we have 4 slots on our shelf. The first slot, there's 10 choices. We have 10 trophies. Second slot, there's 9. Third slot, there's 8. And the fourth slot, there's only 7 trophies left to choose from. Well, rather than writing that definition out as 10 times 9 times 8 times 7, what we can do is this. With what we've learned of factorials, we can write that as 10 factorial divided by 6 factorial. The 6 factorial is dividing out the times 6 times 5 times 4 times 3 times 1 that would have come after the 7 in our 10 factorial. Well, this is a permutation of 10 things where we're only choosing 4 of them. That's 10 factorial, and the 6, I'm going to write it as 10 minus 4 factorial. So the formula, as we saw last class, for a permutation of n things where we're going to use r of them is n factorial over n minus r factorial. So we have 26 letters that we're going to use to make license plates. We cannot repeat any of them now. So it'd be 26, 25 for the second one, and 24 choices for the third one. That's a permutation of 26 items, and we're only going to use 3 of them. Now again, this notation only applies when it's not replaced, without replacement. We cannot reuse them. So this is 26 factorial over 26 minus 3 factorial. So let's do that calculation. That's 26 factorial. Hopefully on your calculators, most of the TI-30s have that factorial button as a second function, so it's a little easier to get to than having to go through the math menus like I do. 26 factorial divided by parentheses, 26 minus 3, close parentheses, factorial. 15,600 different combinations of those letters. You can see if we'd multiplied them out, we'd come up with the same thing. What if we did allow the numbers to be repeated? So this was without replacement. What if we allowed with replacement? So the numbers could be repeated. Well, that's just 26 times 26 times 26. That's just the number of possibilities to the power of the number of items chosen. And you see that that's a slightly higher number, 17,576 items. So that's permutations. Let's talk about combinations. The combination is what we used as our binomial coefficient. In a combination, the order chosen does not matter. So the order chosen or arranged does not matter. So this time, rather than choosing trophies to put on the shelf, we're going to choose 3 out of 10 trophies to throw away, to discard. Well, now it doesn't matter which one's chosen first, which one's chosen second, or which one's chosen third. They're all going to get thrown in the trash. So the order that they're chosen doesn't matter. And again, we're assuming order chosen is the order arranged. Really doesn't change anything here. The formula for a combination, the combination of n things chosen r at a time. And again, this is without replacement. And that is n factorial over r factorial times n minus r factorial. You'll notice that formula is very similar to our permutation formula. The permutation formula, I'll write it off to the side here again. A permutation of n things where we're choosing r of them was n factorial over n minus r factorial. You can see in this one we divide by that extra term of r factorial. R factorial is just the number of ways you could arrange those things. In this case, r is 3, the number of ways you could have arranged 3 things. There would have been 3 choices for the first, 2 for the second, 1 for the third. We're dividing out the number of different arrangements. So the number of arrangements doesn't matter. It's just what's in the group that matters, not what order they're in. Order does not matter. So that's where that extra term of dividing by that r factorial comes from. So for this one here, we're going to choose 3 out of 10 items. So this is a combination of 10 items where we're choosing 3 of them. So n is 10, that's 10 factorial over r is 3, so that's 3 factorial. And n minus r will be 10 minus 3 factorial. So 10 times 9 times 8 times 7 times on down. The reason I stopped at 7, well, we got the 3 factorial here will be 3 times 2 times 1. But then we got the 10 minus 3 is 7. That'll be 7 factorial. 7 times 6 times all the way down. And we notice that 7 factorial cancels out all these terms from 7 on down. So we got 10 times 9 times 8 divided by 3 times 2 times 1. I'm going to do some cross canceling. The 10 I'm going to leave alone, but the 3 and the 9 I'm going to cross cancel. 9 divided by 3 is 3. The 8 and the 2, 8 divided by 2 is 4. So this is 10 times 3 times 4. There's 120 ways. Out of those 10 trophies, there's 120 ways. We could choose 3 of them to discard. So the question is, when is it a permutation? When is it a combination? Well, let's look at our fictional math club. Let's say our math club gets 15 members. For our first example, we need to choose from those 15 members a president, secretary, and a treasurer. And we're going to choose them in that order. President first, then secretary, then treasurer. Does the order of selection matter here? Well, of course it does. Being chosen president is different than being chosen secretary or being chosen treasurer. So yes, it does matter what order these are chosen in. So this is a permutation. Oops, not what I wanted. And it's a permutation. We have 5 items to choose from, and we're selecting 3 of them. So permutation of 15, chosen 3 at a time. So this is 15 factorial over 15 minus 3 factorial. I'm just going to punch this in the calculator. 15 factorial divided by 15 minus 3 factorial. Give us 2,730. So there's 2,730 different ways of choosing those 3 officers from that club. The second question I'm going to ask is we just want to choose 3 members to go to a conference. So here the order does not matter. All 3 members get to go to the same conference. Doesn't matter if they're the first one chosen or the third one chosen. They're going to the conference. So this is a combination. This is a combination of 15 items to choose from, where we're choosing 3 of them. So this will be, scroll up a little bit so you can see better, 15 factorial over 3 factorial, 15 minus 3 factorial. So the 15 factorial, of course, is 15 times 14 times 13 times 12 times 11 on down. 3 factorial is 3 times 2 times 1. 15 minus 3 is 12, so that's 12 factorial. That'll be 12 times 11 times all the way down. Once again, we see the 12 factorial cancels out the 12 on down on top. And let's do the 3 and the 15. We'll divide out. 15 divided by 3 is 5. 14 will divide by 2, that's 7. And the 13 is not going to change. So that's just 5 times 7 times 13, giving us 455. Well, you might ask, well, why couldn't I just punch that in the calculator instead of trying to reduce? You could have. You could have done 15 factorial divided by, but you got to be careful on bottom. You got to put this in parentheses. Divided by, in parentheses, you're going to do 3 factorial times, now I'm just going to do the math, 15 minus 3 is 12. 12 factorial. So notice the 3 factorial times 12 factorial is in parentheses, so that we're keeping that on the bottom of that fraction. And it does still come out to the 455. So let's look at another possibility here. Let's look at the big lotto. The big lotto is going to be 3 numbers. So we're going to call it the big 3 lotto. So you have to choose 3 numbers. Our first possibility we're going to put up here is, first of all, numbers are chosen. We're using the ping pong balls, but numbers are chosen. Oops, not chosen, chosen. From 3 separate tumblers, or whatever we want to call it. We'll just say 3 separate bins. And you must match them in order. Well, if you must match them in order, the fact that it says in order tells us this is a permutation. 3 separate bins is telling us the first bin has the digits 0 through 9. Second bin has the digits 0 through 9. Third bin has the digits 0 through 9. So this is with replacement, because you can select a digit over again. So in this first digit, there's 10 possible numbers for that first one. The second one has also 10 possibilities because it's from a separate bin, and the third one also has 10 possibilities. That is just 1,000 possible combinations. So it gives you an idea of your chances to win. Our second possibility, chosen from 1 bin, must match the numbers in any order. So as long as you have those same 3 numbers, the order you have them does not matter. Well, since the order doesn't matter, this is a combination. This, since it's chosen from 1 bin, once the number is chosen from the first one, the second one, there's 1 less possibility. And the third one, the second less possibility. So this is without replacement. So far, all of the combinations we've talked about have been without replacement. And the formula for combinations is assuming that it's without replacement. That combination of n things chosen R, when we're choosing R of them, assumes no replacement. So in this case, that's going to be a combination of 10 numbers 0 through 9, and we're choosing 3 of them. So that's going to be 10 factorial over 3 factorial, 10 minus 3 factorial. So 10 factorial divided by, in parentheses, 3 factorial times 10 minus 3 is 7 factorial. Close that parentheses. We get 120 different ways of choosing that. Much better chances than 1,000 different ways of choosing in this first one. Third, they're chosen from one bin again. Again, we're going to match in order. So once again, matching in order tells us this is a permutation. Chosen from one bin, so once we choose a number from it, it's no longer in the bin. This is without replacement. So this is that formula for permutation again was for the without replacement. So this is going to be a permutation of 10 items where we choose 3 of them. So that's 10 factorial over 10 minus 3 factorial. So to punch this in the calculator is quite a bit easier. Just 10 factorial divided by 10 minus 3 is 7. So 7 factorial, giving us 720 possibilities. Now, our textbook doesn't mention it, but it is possible to have a combination where the order doesn't matter with replacement. Well, it doesn't, you think about it, it doesn't make sense in most cases. If you're choosing, a combination, you're choosing your group, and everybody in the group is going to have the same recognition. With replacement, doesn't make sense in most cases for combinations. But let's say you're going to give out $100 prizes to each person drawn. Well, if you draw a person out and give them a $100 prize, draw the next person out, give them a $100 prize. The order they're chosen doesn't matter. But it does matter if you choose them, they get a $100 prize, and you throw their name away. They can't win a second time. That's our standard combination without replacement. That's what we've been doing. That's without replacement is that formula we've been looking at. Combination of n chosen r, n factorial over r factorial, n minus r factorial. That's that standard formula for a combination. If it's with replacement, let's say you draw their name out, they get the $100 prize, you put their name back in, they can win multiple times. That's with replacement. In a combination with replacement, we just say C, we put a big R by it to say combination with replacement of n things, and we're going to choose R of them. Well, now it's the number of possible choices that's increased. By putting their names back in to the bin, we're increasing the number of items to choose from. So it is now going to be n plus r minus 1 factorial over r factorial n minus r factorial. Again, that's not something we use in this course, but I wanted to throw it out there for you so that you've seen it. Okay, it's 10:22. It is our break time. Let's take our break. We'll come back at about 10:30 and we'll pick up from there. So the next step, the second part of the class, we're going to talk about basic probability. There are 3 types of basic probability. There is subjective, there is empirical, sometimes called experimental, and then there is theoretical. Subjective probability is really just that. It is based on previous events and prior knowledge. But what it really comes down to is it's really an educated guess. Somebody is, when we look at the probability of Team A winning a football game, well, we look at the history. These two teams have played this many times in the past, and Team A has won this percent of the games. And so far this year, Team A has this record and Team B has this record. Team A has won so much percent of their games on the road. Team B has lost this many at home. Those things are taken into consideration, but when it comes down to it, we really don't know how well they're going to perform on a given day. So it is still an educated guess. The empirical or experimental is based on past experience. And really what it's based on is relative frequency. Oops. What do I mean by that? Well, let's say that we flip a coin 600 times and we get heads on that coin. $246 of those 600 times. That would indicate to us that the probability of getting heads, and we're going to introduce some notation here. Probability of getting heads the notation, we're going to give capital P, and then we'll put heads in parentheses. So that's saying the probability that the result of that event will be a heads. So the next time we flip the coin, the probability of it coming up heads, well, we've had 246 heads in the past out of 600 attempts. We divide that out, 246 divided by 600 should be 0.41. So the empirical or experimental probability of getting heads on that coin is 41% or 0.41 probability. The theoretical or computational probability relies on something called equally likely outcomes. So if each possible result is equally likely, so equally likely means if each possible result has the same probability of occurring, or the same chance to occur. Then the probability of having a result that has a certain characteristic. So the probability of having a result with characteristic A is just equal to the number of results that have the characteristic A over the total number of results. Well, what does that mean? Well, flipping a coin, the probability of getting heads, if we assume heads and tails are equally likely, there's one result that gives us heads out of two possible results, heads or tails. We are ignoring the very, very, very slight possibility that the coin lands on its edge. I always have students that bring that up. Yes, it is possible, but it is so small of a possibility that we can ignore it and it doesn't affect our numbers a whole lot. Equally likely could be rolling a die. If you've worked with dice before, you know that supposedly a fair die, each side has the same probability of occurring. So the probability of rolling a 2 Well, each die has 1 2 out of it on it. One side has a 2 on it out of 6 different numbers. So it's a 1/6, or if we divide it out, 0.1667 probability. Generally, probabilities get stated to 4 decimal places unless it tells you otherwise. We could have a probability for rolling a die. Let's say the probability of rolling an even number. So an even number is 2, 4, 6, 8. On the die, there are 3 even numbers, 2, 4, and 6, out of 6 total. So that's a 3 out of 6, which you reduce to a 1/2. And sometimes the fraction is preferable for the probability, or we can divide it to be a decimal of a 0.5 probability. Well, let's look at those marbles in a box. And again, we're going to go with 3 red and 2 blue. So my first question I'm going to ask, what is the probability of reaching in there and getting a red marble? I'm just going to use R for red. Well, there's 3 red marbles out of 5 total. 3 out of 5 are a 0.6 probability. Second question I'm going to ask, assuming it's all back to the 3 red and 2 blue again, what's the probability of reaching in there and getting a blue? Well, there's 2 blue in there out of 5 total. So a 2 out of 5 are a 0.4 probability. Well, that's not very interesting so far. What if I ask you the probability of getting neither red nor blue? Well, all of them are red or blue, so there's 0 marbles in there that are not red or blue out of 5. So that's a 0 probability. What does that 0 probability mean? Well, 0 probability. Probability of an event X is 0. That means X is not possible. It is not possible for that to occur. What if I ask for the probability of a red or a blue marble? Well, red or blue, there's 3 red and 5 blue, or 2 blue, I should say. So it's 3 could be red plus 2 blue out of 5. So that's a 5 out of 5, or a probability of 1. A probability of 1, if P of X equals 1, that means it will definitely happen. So either it's something that's already occurred, so we know it had to happen, or it just contains all of the possible results, so one of those results has to occur. So it's definitely going to have its conditions met. What would be the probability of reaching in there, grabbing 1 marble, have it being red and blue? Well, it's not possible for a marble to be both. This is impossible. So there's 0 marbles that are both red and blue out of 5 total. It's a probability of 0. Just like we said, it's impossible. So from what we've seen here, we see that our probabilities have to be between 0 and 1. If it equals 0, it's impossible. If it equals 1, it's definite. Most probabilities fall somewhere in between there in that range. Well, these were single events. We reached in, we grabbed 1 marble. We were looking at 1 result. But often we're looking at multiple results happening together. So we're going to talk about compound events. Now it's a little confusing because what we talked about here, this was still just a single event. We were only choosing 1 marble, but we wanted it to have, we were combining 2 possible characteristics, possible outcomes in that single event. The OR was possible because we only need one of the two things to happen. If either one of them happens, we've met that condition. The and requires us to meet both conditions. And in this example, it wasn't possible to meet both conditions. We'll look at other possibilities where we can meet both conditions. This idea here, saying we wanted that marble that we drew to be red and blue, is something we refer to as mutually exclusive. If one is true, the other one cannot be true. So if the marble is red, it cannot be blue, and if the marble is blue, it cannot be red. So there's no way it can be both. Once we know that one of them is true, the other one can't be. So the probability of those mutually exclusive events happening together is always 0. So compound events, we are looking at 2 events happening. And so we got separate conditions for each event. So for compound events, let's say we're going to reach in and draw out 2 marbles. Now, just like with our permutations and combinations, when we're selecting more than one thing, it does matter that with replacement or without replacement becomes a factor again. So let's do a 6th problem here. What is the probability of reaching in and grabbing a red marble for a first one? And a second one is also red if this is with replacement. So that means we draw the first marble, we see whether it's red or blue, and then we put it back in. So the probability of the first one being red was 3 out of 5. The probability of the second one being red is 3 out of 5. Our fundamental counting principle applies here. We can just multiply the probabilities if we want to. There's 3 successful outcomes times another 3 is 9. 5 total possibilities times another 5 total possibilities is 25. So 9 out of those 25 possibilities would give us 2 heads, or 2 reds, or a 0.36 probability. How would that change if it was without replacement? So what's the probability of drawing a red followed by another red if it's without replacement? Now, sometimes the wording on this can be a little tricky or a little subtle. You have to read between the lines. If we say we reach in and we grab 2 marbles, what's the probability that both of them are red? Well, there it's without replacement, because if you're drawing 2 marbles, you didn't have time to put the first one back before you drew the second one. You're drawing 2 marbles at the same time. That would be without replacement. So for the first one, there's 3 red out of 5. That's the probability of the first one being red. For the second, though, now the question comes up, well, how do we know if the first one was red? We don't know, but what we do know is if the first one wasn't red, it doesn't matter what the second one is, we'd be done. So we have to assume that the first one was red. Because if it wasn't red, we wouldn't worry about the rest of the calculation. So we have to assume success in the first event before we can find the probability of that second event. So assuming the first one was red, when we draw the second marble, there's only 2 red marbles left out of 4 total. So 3 times 2 is 6, 5 times 4 is 20. That is 6 out of 20, or 0.3 is that probability. 0.30 if we want to compare them. Notice that probability is significantly less than if we were using replacement. Well, let's look at a little bit more interesting compound event. Let's say we're going to roll a die and flip a coin. I want to find the probability of rolling a 5 and flipping tails? Well, that's just going to be the probability of rolling a 5 on the die times the probability of flipping tails on the coin. These are independent events. What occurs on the first event does not affect the probabilities of the second event. Whatever that die comes up when we roll it, it's not going to change the probability of getting tails on the coin. So the probability of getting a 5 on the die is 1 out of 5. Probability of getting tails on the coin is 1 out of 2. So 1 times 1 is 1, 5 times 2 is 10, 1/10, or a 0.1 probability. So if we go back up here, with replacement, that is independent events. Because the probability of getting a red marble on the second draw is not affected by the first draw. If we got a blue marble on the first draw, we put it back in, the probability of getting red on the second draw is still 3 out of 5. Or if we get a red on the first draw, it doesn't matter, we put it back in before we do the second draw, the probability of a red marble on the second draw is still 3 out of 5. This one down here, though, number 7, is dependent. Now, some textbooks use the term dependent event. Some just say not independent events. A very subtle difference, but we can say dependent here. Because the probability of drawing a red marble on this second draw does depend on the result of the first draw. Technically, what we are saying here is this is the probability of getting a red marble on the second draw given that we had red on the first draw. Because if the first one wasn't red, that second probability would be much different. But if the first one wasn't red, we don't care because we're not going to get our condition of 2 red. Another place where probability is used a lot is in business contingency tables. Let's look at a table like this. What's the probability of getting, let's look at students who have an A in the class or not an A in the class up until the point of the final exam. And over here, we have A on the final exam and not an A on the final exam. So let's say that in this table we have, and we're going to use a larger class just to make the numbers a little more useful. So let's say in a bigger class, we have 6 students. Let's do this. Let's say that we have 6 students that had an A going in the class and also got an A on the final. And we had another 8 who had an A going in the class but did not get an A on the final. Of those that were not getting an A in the class, we had 4 of them get an A on the final exam. We had 32 of them not get an A on the final exam. This is what we refer to as a contingency table. And what it does is it compares 2 variables. The first variable here, having an A in the class or not having an A in the class. Second variable, getting an A on the final compared to not getting an A on the final. To work with a contingency table, we usually need to find both row totals and column totals. So this would be our row totals here. 6 plus 8 is 14. 4 plus 32 is 36. This would be our column totals. 6 plus 4 is 10. 4 plus 32 is 40. And then this would be the grand total. 10 plus 40 is 50. 14 plus 36 is also 50. It better add up in both directions. Most probabilities that we would calculate from this, or many probabilities I should say, just involve one of these totals and the grand total. For example, if we ask, assuming that if we randomly select, it's equally likely to get any student, what is the probability that a randomly selected student now let's ask her a question. Is getting an A in the class. So the probability of getting an A in the class, I was going to say A class. Well, there are, up here we see there's 14 students that are getting an A in the class out of our 15 grand total. That's 14 out of 50 grand total. 14 out of 50, or I can divide that to be a 0.28 probability. I might ask, what's the probability that a randomly selected student does not get an A on the final? So this is our probability. Computer's working really slow here today, sorry. Probability of not an A on the final. When we look up here, there's 40 students who will not get an A on the final out of that 50 grand total. So that's 40 out of 50, or a 0.80 if you want to go another decimal place, probability. So notice in each of those, we used a row total or a common total, or column total, along with the grand total. Well, let's make it a little bit more complex. What's the probability that a randomly selected student has an A in the class and an A on the final? So this is a probability of A in the class and A in the final. Well, if we look up above, A in the class, that's these. A in the final, that's those. So I'm adding those three, oops, sorry, not those. So the ones that meet both are those 6. They have both an A in the final and an A in the class. So there are 6 that do both out of 50. So that's 6 out of 50, or a 0.12 probability. A little bit tougher to calculate, which is weird because it seems almost like an easier problem, would be what's the probability that randomly selected student has an A in the class, or, so that's the big difference here is that's an or, an A on the final. Now that does not exclude both. They could have both an A in the class and an A in the final. But this is a probability of A in the class or an A in the final. So if we look at those again going up here, well, once again, these are the ones that have an A in the class, and these are the ones that have an A in the final. Or means either one of them. So now we're adding up all 3 of those values, not just the ones where they overlap. So 6 plus 4 is 10, plus 8 is 18. That's 18 out of 50. or a 0.36 probability. Now, there is a shortcut, a possible shortcut for this one. Because if we look at this, you might be thinking, well, we had 10 that had an A on the final and 14 that had an A in a class. Why don't we just add them up and have 24 students? Well, the problem is these 6 that did both were counted twice. So what we could have done was we could have done A in the class plus the A in the final, and then subtracted out those that had an A in both. And of course, out of 50. So that would have been the 14 that had an A in the class, plus the 10 that had the A on the final, minus the 6 that did both, had an A in the class and an A on the final. Well, 14 plus 10 is 24, minus 6 is 18. That's still 18 out of 50. Not part of this course, but this is called the inclusion-exclusion principle. Rather than going through and adding up the individual probabilities, which in this one it's not a lot, there's only 3 of them to add up. But if you had 4 categories in each direction or more categories in each direction, it could be quite a few to add up. You could just take the totals for each and then subtract out where they overlap. That's the exclusion part. Well, now we want to talk about conditional probability. Conditional probability, what happens in conditional probability is we add a condition that limits the population. So in this case, we might not be looking at all 50 students anymore. We'd only be looking at a certain portion of them. Well, what does that mean? Let's say we want to find the probability that a randomly selected student has an A on the final given, that's the key word there, given they have an A in the class. So what does that mean? Well, the given means we are narrowing our search. We're only going to be drawing from the students that have an A in the class. So if we're going up here, I'm going to erase some of my mess here quick. We're not looking at all 50 of these anymore. The given that they have an A in the class means we're only looking at those that have an A in the class. We're only looking at those 14. Of those 14, 6 of them had an A on the final. So the probability of getting an A on the final, given that you had an A in the class, is 6 out of 14. Now that is going to divide out to be 4285714.3 approximately. Typically around to 4 decimal places, so 0.4286 is that probability. Or you could reduce the 6 over 14 down to a 3/7. It's not necessarily the same to ask this conditional in reverse. Let's say we ask, what is the probability they have an A in the class given they have an A on the final? So what this means is we are limiting ourselves to those that had an A on the final exam. So it's slightly different if we go up here to our table. Rather than limiting ourselves to these 14 that had the A in the class, we're limiting ourselves to these 10 who got an A on the final. Of those 10, 6 of them were getting an A in the class prior to that. So that's 6 A's out of the 10 that got A's on the final. That's a 0.6 probability. Notice that number is quite different. Any questions? Okay. Well, we've looked at the binomial coefficient, binomial expansion last class. There's something called binomial probabilities. And binomial probabilities are where we have a constant probability of an item having a certain characteristic. For example, let's say that 12% of students earn A's in their math class. My percent is quite a bit higher than that, but let's just go with that for now. So that means each student walking in the door has a 12% or 0.12 probability of having an A in that class. In a class of, let's say, 15 students, find the probability and let's say of 4 A's, 4 students earning A's. Well, there is a binomial. That binomial coefficient comes into play again. The binomial coefficient for this is 15 students choosing 4 of them to receive A's. Now the rest of it is the probability of success. That's a 0.12 is the probability that they'll have A's. We want 4 of them to have A's. And the probability of failure, 0.88. There's 88% of them that will not get A's, and we want 15 minus 4, or 11 of them to not have A's. That's the rest of that probability. Now, we're not going to require, you're not going to be tested or quizzed on that in this course. But I wanted you to see that there is a connection between binomial probabilities and the binomial expansion that you would receive doing your polynomial expansion. One last thing we want to cover, and then I'll let you go for the day. And that is, out of these, this example, let's keep going with this binomial example. It's a great place to use it. What if we want to find the probability that less than 4 have A's? Well, to do that, we need to find the probability that 0 will get A's, plus the probability that 1 gets an A, plus the probability that 2 get an A, plus the probability that 3 gets an A. Now, less than 4 does not include 4. 4 is not less than 4. So it's only from 0 up to 3. We would have to find those 3 probabilities and add them together. And that's not so bad to do. But what if I asked you for the probability of no more than 11 have A's? Well, what we'd be looking at there, that's the probability of 0 plus the probability of 1 plus the probability of 2 all the way up to the probability of 11. Well, if you include the probability of 0, there's 12 different probabilities that have to be calculated there. Well, we know that if we add up all the possibilities, if I add on to this the probability of getting 12 all the way up to that probability of getting 15, all of those probabilities have to add up to 1 because it's guaranteed that one of those is going to occur. So if we know that they all add up to 1, and I want to know the probability of no more than 11 getting A's, rather than finding these 12 probabilities and adding them up, I could find these 4 probabilities. The probability of getting 12, 13, 14, or 15. And then I could subtract that probability Once I have that probability there, I can do 1 minus that to get this probability. This number here, or this group here, is called the complement of that group. Between the two of them, they contain all of the possibilities for that experiment, for that event that we're doing. So if one of them doesn't occur, the other one has to. So the probabilities of complements, an event, let's call it A plus the complement of A. The notation for that is a bar over A. So the probability, A is the event, A is its complement. So the probability of A occurring plus the probability of its complement occurring is always 1. Because a complement is defined to be that if A doesn't happen, its complement must happen. Let's look at a simpler example. Rolling a die again. Well, let's say we want to know the probability of rolling a 2. So rolling a 2 is the event. Well, there's 1, 2 out of 6 possibilities. The complement of that would be the probability of rolling a 1, 3, 4, 5, or 6. Everything but the 2. Well, that's 5 out of 6. There's 5 possibilities out of 6 total. Notice those two, 1/6 and 5/6, add up to 1. Those are the complements. And in probability, when we're doing complex events, sometimes it's easier to find the probability of the complement and subtract it from 1, like we showed up here. Instead of finding 12 probabilities here, we found 4 probabilities for the complement and subtracted that total from 1. Okay, I will stop babbling now. Remember, you do have a quiz due today. You have an old homework from Monday that's due tomorrow, due Thursday. And you have a new homework from today that'll be due next week, Tuesday. That is all of the new material for the course. On Monday, we plan to do a review basically for this final test. There's a lot of stuff in this course, in a wide variety, going from all the algebra and all that into the trig and the conic sections, and then now into this, counting principles and probability and series and sequence. A lot of different topics in this course. So I want to make sure you remember all the important stuff and are ready for the final exam. Also remember, there is a final exam review out there. In my math lab that is worth up to 20 points. Extra credit. So that is also a great review. I actually designed that review to cover all the questions and more that could be on the final exam. So if you do that review and you're doing well with it, you're pretty well prepared for the final exam. Anybody have any questions? Okay, well, you all have a great day, and we will see you on Monday.